Chapter 1, Fundamentals of Testing. In this chapter, we will discuss several fundamental aspects of software testing. We will begin by defining what testing is and exploring why it is a necessary component of the software development process. Next, we will examine the 7 key principles of testing that guide effective practices. Following that, we will delve into various test activities, the importance of testware, and the different roles involved in testing. Finally, we will touch on the psychology of testing, which influences how testers approach their work. What is testing? Software systems are an integral part of life. Almost everyone uses software each and every day. From business applications, for example, in our banking transactions when we buy things, to consumer products, for example, cars with embedded software. Most people have had an experience with software that did not work as expected. Software that does not work correctly can lead to many problems, including loss of money, time, or business reputation, and even injury or death. Software testing is a way to assess the quality of the software and to reduce the risk of software failure in operation. A common misperception of testing is that it only consists of running tests, that is, executing the software and checking the results. Another common misperception of testing is that it focuses entirely on verification of requirements, user stories, or other specifications, which we will later talk about. As we will see later in this course, software testing is a whole process that consists of many different activities. Running, or as we say executing, tests is only one of these activities. There are more activities such as test planning, analyzing, designing and implementing tests, reporting test progress and results, and evaluating the quality of what we are testing. Some testing does involve the execution of the component or system being tested. Such testing is called dynamic testing. Other testing does not involve the execution of the component or system being tested. Such testing is called static testing. Testing also includes reviewing work products such as requirements, user stories, and source code. While testing does involve checking whether the system meets specified requirements, it also has to be validated. We need to check whether the system will meet user needs or other stakeholder needs when it operates. Test objectives. For any given project, the objectives of testing may include to prevent defects. The objective here, what testing is about, is to prevent defects. So to prevent defects, we need to evaluate, to assess, to check out some of what we call the work products or the products of our work. Work products can be the code or the design or other things such as the requirements or the user stories, things that we will talk about later. Another objective of testing is to verify whether our software fulfills all the requirements. So if we wanted to verify the requirement that we just described, we should try using a valid username and password and see if it works. See whether it takes us from the login page to that user's personal page. Another objective is to check whether our test object, the software we are testing, is complete. It doesn't miss any features, and make sure, validate, that it works as its users would expect. And also as everyone else that has any connection or is affected from this software would expect. Those people are called the stakeholders, and they can be the developers, the designers, the managers, the partners, the customers, and so on and so forth. Another goal when we are testing is to become more and more confident that our test object has high level of quality. A question that arises many times in testing is, how much testing is enough? How high is the level of the quality of our product? Is it good enough? While obviously there is not a clear answer to that question, and of course the more testing the better, we do not always have the luxury of the budget or the time or the resources or the people to keep testing our software. But the more methodic we are, the better results we will have and the more confident we will be in creating reliable software of great quality. Another goal of testing is to reduce the risk that our software is not of high quality. And we achieve this by finding defects. And we actually can say that the more defects we find, the less is the risk that our software is of inadequate quality. We are also testing because we want to provide information to the stakeholders. We need to let them know everything about the software, how it works, if it works as expected, so they can make informed decisions For example, when the developers know that something is not working as expected, they need to fix it, to do debugging as we call it. Or if everybody is confident that the quality is high, then the software can be released to the world to use it. There are many different standards that a project may need to comply with, or in simple words, many different rules that it should follow. An example is the GDPR, or General Data Protection Regulation, a legal framework in the European Union that is set to protect the personal data of the users of any application. Each level of testing also has different goals. Later, we will learn that in component testing, one of the goals is to increase code coverage. Code coverage is the amount of software code that a test is covering, meaning that if the test passes, then that piece of code works correctly. On the other hand, in acceptance testing, which is a higher level of testing, one of the goals is to inform the stakeholders about the risk of releasing the system, so they can decide whether they should release it now or just do some more testing to become more confident. In general, we could say that testing is about finding the defects, while debugging is about finding, analyzing, and mostly fixing the defects. And in the developer's language, defects are called bugs and are related to the code, while defects are in the tester's language and are more related to the customer experience. So defects and bugs are actually the same, but from another perspective. Also, very important for testing is to check again if the fixes done in debugging have actually resolved the defects or not. Executing tests can show failures that are caused by defects. So defects can actually cause software failures, and failures can be devastating, for example, data loss or exposure of user data or attack by hackers in. Insecure systems or a totally unresponsive system. Critical failures are usually caused by accumulated defects. Similarly, the debugging process consists of reproducing the failure, then finding the root cause, which is called diagnosis, and finally fixing the root cause. Throughout the history of computing, defects have caused failure to software and systems, and that means that those software or system couldn't finally meet the stakeholders' needs. However, using appropriate test techniques can reduce the frequency of such problematic deliveries when those techniques are applied with the appropriate level of test expertise, in the appropriate test levels, and at the appropriate points in the software development lifecycle. When we perform rigorous testing of our components, our systems, and their documentation, we reduce the risk of failures that may occur during operation. When defects are detected through testing, and then those defects are fixed, this contributes to the quality of the components or systems. In addition, software testing may also be required to meet contractual or legal requirements or industry-specific standards. When we have testers involved in requirements reviews or user story refinement, then they could detect defects in these work products. A user story is a concise description of a feature from the user's perspective, highlighting their needs and goals. For example, as a user, I want to upload my CV on the website so that potential employers can view it. This format helps teams understand what users want and why it's important. So when testers identify and remove the requirements defects or refine user stories, they actively help reduce the risk of developing incorrect or untestable features. When testers work together with the system or software designers, they increase their understanding of the system's design, which means that they better understand how to test the system. And when testers understand the design of the system, they reduce the risk of fundamental design defects and help find those defects at an early stage. When testers work closely with developers while the code is under development, that increases both their understanding of the code and how to test that coder. This increased understanding can reduce the risk of defects within the code and the tests. When testers verify and validate the software prior to its release, they can detect failures which might have been missed otherwise. That also will support the process of removing the defects that caused the failures or the debugging. Again, this will increase the likelihood that the software meets stakeholder needs and satisfies the requirements. While people often use the phrase quality assurance or just QA to refer to testing, quality assurance and testing are not the same, but they are related. A larger concept, quality management, ties them together. Quality management includes all activities that direct and control an organization with regard to quality. Among other activities, quality management includes both quality assurance and quality control. Quality assurance is typically focused on adherence to proper processes in order to provide confidence that the appropriate levels of quality will be achieved. When processes are carried out properly, the work products created by those processes are generally of higher quality, which contributes to defect prevention. In addition, the use of root cause analysis to detect and remove the causes of defects, along with the proper application of the findings of retrospective meetings to improve processes, are important for effective quality assurance. Quality control involves various activities, including test activities, that support the achievement of appropriate levels of quality. Test activities are part of the overall software development or maintenance process. Since quality assurance is concerned with the proper execution of the entire process, quality assurance supports proper testing. Testing contributes to the achievement of quality in a variety of ways. Errors may occur for many reasons, such as time pressure, or because someone was not so experienced, or there was not correct communication, usually about requirements or design, or because the code was too complex, we used really advanced and unfamiliar technologies, or we didn't understand how the components of the system should work together, or just because we are humans. So here we should remember that humans make errors. Errors made by humans introduce defects in the system, and those defects make the system behave in unexpected ways. Defects are also known as faults or bugs. So defects or faults or bugs describe the inability of the system to operate as we would expect it to. For example, an error during coding a robot might introduce a defect of the robot being unable to move diagonally. If a defect in the code is executed, this may cause a failure, but not necessarily in all circumstances. For example, some defects require very specific inputs or preconditions to trigger a failure, which may occur rarely or never. Failures can also be caused by environmental conditions. For example, radiation, electromagnetic fields, and pollution can cause defects in firmware or influence the execution of software by changing hardware conditions. Not all unexpected test results are failures. The way we execute a test may cause false positives or false negatives. False positives are reported as defects while they are not defects, while false negatives are unreported defects due to a wrong test output. The best way to clearly define errors, defects, and failures is the following. Errors are made by humans and introduce defects in the system. These defects in the system might cause failures, which will be experienced by the end user. The root causes of defects are the earliest actions or conditions that contributed to creating the defects. We must analyze the defects in order to identify their root causes and reduce the occurrence of similar defects in the future. By performing what we call root cause analysis, we focus on the most significant root causes. This will eventually improve the whole process and prevent introducing a significant number of future defects. Suppose, for example, we have a Google Maps application that should help users find the quickest route to their destination. The developer might not be familiar with shortest paths algorithms. If we have a big number of defects due to similar issues, it might be wise to train better our developers in this area so we won't have so many similar defects in the future. In this example, the customer complaints are effects. The incorrect route proposed by our application is the failure. The improper calculation in the code is a defect, and it resulted from the gap in the developer's knowledge. The root cause was the gap in the developer's knowledge. It is really important to make clear from the beginning that when we perform testing, it can show that there are defects. But no matter how much testing we will perform, we can never prove that there are no defects. What testing actually does is reducing the probability of undiscovered defects that may still remain in the software, but even if we don't find any defects, that doesn't mean that there are no defects. Testing is not a proof of correctness. We also need to understand that most of the times it is impossible to test everything, meaning to test all different combinations of inputs and preconditions. Only except if the system is completely trivial, we would be able to do so. However, what we should do is to perform proper test techniques, risk analysis, and also have the correct priorities in our testing, instead of trying to exhaustively test the system. To find defects early, we should start testing as early as possible in the software development lifecycle. The software development lifecycle is a structured process that outlines the stages of software development, including analysis, design, development, testing, deployment, documentation, and maintenance. Testing early in the software development lifecycle helps reduce or eliminate costly changes. Usually, when we are testing just before we release the software in a stage that we call pre-release testing, we find that a small number of modules, a small number of parts in the system, usually contains most of the defects, or it is responsible for most of the operational failures. This means that defects tend to accumulate to cluster together. When performing risk analysis, it is really important for testers to be able to predict defect clusters and put their efforts there. If we keep repeating the same tests, eventually these tests will no longer find any new defects. To detect new defects, we may need to change existing tests and their data, or we may even need to write new tests. This is kind of similar to pesticides that are no longer effective at killing insects after a while. Testing is done differently in different contexts. For example, we will perform different kind of tests to an airport control software system and to an e-banking mobile application. The context is always very important in defining the test process. Some organizations expect that testers can run all possible tests and find all possible defects, but principles 2 and 1, respectively, tell us that this is impossible. Further, it is absolutely wrong to expect that just by finding and fixing a large number of defects, that will ensure the success of a system. For example, even though we have fixed a great number of defects, a system might still not look like what its users expected. And this means that we should keep refining our system until it makes its users satisfied. In the following sections, we will describe general aspects of organizational test processes in terms of what we call test activities and tasks, test work products, and also traceability between the test basis and testware. The test basis are all the foundational documents used to design and execute tests, so we can early detect defects and reduce the need for costly changes later in the software development lifecycle. It is very useful if we can create measurable coverage criteria for our test basis. These criteria can act effectively as key performance indicators, which can drive our activities and check if we have achieved our testing goals. For example, for a mobile application, the test basis may include a list of requirements and a list of supported mobile devices. Each requirement is an element of the test basis. Each supported device is also an element of the test basis. And then we can create our tests, say one test for each requirement, but repeat each test for every different mobile device. In that way, we can see how our system performs, and we can inform all stakeholders. While every software project is unique, there are common steps that testers go through to ensure applications work properly. These steps are known as test activities, which together make up the testing process. Some key activities include developing test plans, creating test cases, executing those tests, reporting on bugs found, and retesting once issues are fixed. Testers will tailor which activities they do and when based on factors like the application type, features included, and schedule. During testing, testers use various testware, which are the assets needed to test the software. This includes test cases, test data, and tools to run automated tests. Testers link the testware back to requirements and other source documents through traceability to verify each part of the software is evaluated. Different roles like test lead, automator, and execution tester help split up the activities. Popular software like Google Docs, iPhone apps, and banking websites all rely on testing processes to ensure they work for customers as intended. The ISO standards provide detailed guidelines so testers approach each project in a thorough, organized way. There are several test activities and tasks, which in turn are composed from other activities. Although these activity tasks may appear that they take part one after another, many times this is not what happens. For example, in agile software development, there are small iterations of software design, build, and test that happen on a continuous basis, supported by ongoing planning. So we must also perform our test activities on an iterative, continuous basis within this software development approach. Even when we have sequential software development, the step these groups of activities may be overlapped, combined, take part at the same time, or some of them can be omitted sometimes. This means that very often we need to tailor these main groups of activities within the context of the system and the project. During test planning, we must define the objectives, the goals of testing, what we want to achieve, and also what will be our approach to meet these objectives. Of course, we would need to consider all kinds of constraints we may have. Sometimes we may need to revisit and revise our test plans based on the feedback that we have during the monitoring and control activities. Test monitoring actually means to continuously compare the actual progress against planned progress, and for that we will use any test monitoring metrics that we have defined during the test plan. Test control involves taking actions necessary to meet the objectives of the test plan, which may be updated over time. What both test monitor and test control include is the evaluation of the exit criteria, which are the criteria for all testing activities to stop. In some SDLC models, exit criteria are called definition of done. Test analysis involves looking closely at important documents like business requirements, functional requirements, system requirements, user stories, and use cases. It also includes design and implementation details, as well as risk analysis reports. The goal is to find any unclear parts, missing information, inconsistencies, inaccuracies, contradictions, or unnecessary statements. This helps identify which features need testing and allows testers to define and prioritize the test conditions for each feature. Finally, it ensures that everything can be traced back to its source, which improves the overall quality of the software. Test design is the process of creating specific test cases that outline how to evaluate the software. This involves identifying the necessary test data and designing the test environment where the testing will take place. A key aspect of this process is ensuring that everything can be traced back to the original requirements. This careful planning helps ensure that the tests are effective and that the software meets its intended goals. During test implementation, testers create or complete the necessary materials for executing tests, which includes organizing test cases into procedures. While test design focuses on how to test, test implementation ensures that everything is ready to run the tests. Key activities in test implementation involve developing and prioritizing test procedures and potentially creating automated test scripts. Testers form test suites from these procedures and scripts, arranging them for efficient execution. They also build the test environment, which may include tools like test harnesses or simulators, and verify that everything is set up correctly. Preparing test data and ensuring it loads properly in the environment is crucial. Finally, Testers check that all components, such as the test bases, conditions, cases, procedures, and suites, are traceable to one another. Test design and implementation tasks often overlap. In exploratory testing and other experience-based methods, testers may perform these tasks during test execution. Exploratory testing can use test charters to outline testing goals and ideas for execution, allowing testers to design and run tests immediately. During test execution, testers run test suites according to a scheduled plan. This phase involves several key activities. First, they record the IDs and versions of the test items, tools, and materials. Testers execute tests either manually or with automated tools. Next, they compare the actual results to the expected outcomes. If they find any differences, they analyze anomalies to determine their causes, as issues may arise from defects in the code or could be false positives. Testers report defects based on the failures observed and log the results of the test execution, such as pass, fail, or blocked. They may need to repeat test activities due to actions taken for an anomaly or as part of the planned testing, which includes executing corrected tests or performing confirmation and regression testing. Finally, testers verify and update the traceability between the test basis, conditions, cases, procedures, and results to maintain clarity and organization throughout the process. Test completion activities gather data from finished test activities to consolidate experience, testware, and other relevant information. Testers perform these activities at project milestones, such as when a software system is released, a test project is completed or canceled, an agile project iteration is finished, a test level is completed, or a maintenance release is finalized. Test completion includes several major activities. First, testers check whether all defect reports are closed and enter change requests or product backlog items for any unresolved defects at the end of test execution. They create a test summary report to communicate findings to stakeholders. Next, they finalize and archive the test environment, test data, test infrastructure, and other testware for later reuse. Testers hand over the testware to maintenance teams, other project teams, or stakeholders who could benefit from it. They also analyze lessons learned from completed test activities to identify necessary changes for future iterations, releases, and projects. Finally, testers use the information gathered to improve the maturity of the test process. When testing software, testers must take into account the overall project environment and needs. Testing does not happen separately from development. It is an integral part of the process from start to finish. Factors like important stakeholders to please, the development team's skills, strict regulations for the industry, and budget deadlines can all shape how testing is done. For example, financial software may need more thorough testing since errors could cost customers money. A tight timeline might mean automating many tests to cover more ground faster. A new team would need additional training compared to experienced developers. Understanding these contextual details helps determine the best testing approach, such as extensive automation for a safety-critical medical app or detailed reporting for a client with high standards. Popular systems like bank websites and smartphone maps have testing customized to their industries and users. By accounting for stakeholder needs, available resources, and other project-specific aspects, testers can ensure the right level and type of evaluation for any software project. When testing applications, testers produce various documents, files, and other testware to guide their work. Examples of common testware include test plans, which lay out the overall testing strategy. Test cases outline individual checks that will be performed. Testers record any bugs discovered in defect reports. To coordinate their efforts, testers create schedules highlighting who will test what features by which dates. Once testing begins, log files track the detailed results of each test run. Different types of testware support the distinct phases of testing. Early on, risk assessments identify potential issues to watch out for. Automated test scripts allow fast rerunning of common checks. Apps like Google Maps require extensive test data to simulate real-world usage. Project documentation ensures consistency as team members change. Proper organization of testware, like placing automation scripts in source control, helps companies continuously improve software quality for users of systems, ranging from banking sites to video games. Consistent test asset management is key to thorough, efficient testing. Test planning work products typically include one or more test plans. The test plan has all the information about the test basis. Using traceability, we are able to relate the test basis to other work products. Also, the test plan will include the exit criteria of our tests, or definition of done. Test monitoring and control work products typically include various types of test reports, such as test progress reports that the testers need to provide regularly, and also test summary reports that the testers should provide when they complete some milestones. Test analysis work products include defined and prioritized test conditions. Each test condition should be traceable to the test basis. Test design produces test cases and sets of test cases to evaluate the test conditions defined during test analysis. It's often best to design high-level test cases that do not include specific values for input data and expected results. These high-level test cases remain reusable across multiple test cycles with different data while adequately documenting the scope of each case. Ideally, each test case has bidirectional traceability to the test conditions it addresses. Test design also leads to several important outcomes. Testers identify and design the necessary test data, create the test environment, and determine the required infrastructure and tools. However, the documentation of these results can vary significantly in extent. Test implementation generates several work products, such as test procedures with their sequencing, test suites, and a test execution schedule. Once testers complete the implementation, they should revisit the test plan to demonstrate how the test procedures connect to the plan, test cases, and test conditions. Often, testers create additional products like service virtualization and automated test scripts during this phase. They also create and verify the test data and test environment, which may sometimes differ or remain incomplete. The test data provides concrete values for the inputs of test cases and their expected results. After receiving clear directions on using these values, testers can execute low-level test cases, with a test oracle identifying the concrete expected results. In exploratory testing, testers might develop some design and implementation products during test execution, and the documentation can vary. Throughout test implementation, testers may further refine the test conditions they define during test analysis. Ideally, once we complete executing the tests, we can report the status of each element of the test basis and trace them with their associated test procedure. For example, we can say which requirements have passed all planned tests, which requirements have failed tests or have defects associated with them, and which requirements have planned tests still waiting to be run. This enables us to verify that the coverage criteria have been met, and enables us to report the test results in a language that the stakeholders can understand. Test completion work products include test summary reports, action items for improvement of subsequent projects or iterations, change requests or product backlog items, and finalized testware. Maintaining clear connections between all the testing documents and results is important for good oversight of projects, and this is called traceability. Testers want to make sure the software meets customer needs, is safe to use, and gets delivered on time and on budget. During testing, we connect the original software requirements to the specific tests created for each part, any issues we find, and the results that show what passed or failed. This process is called traceability. It ensures that we test all requirements and don't overlook anything. It also highlights which parts of the software still need improvement. For example, tracing each bug back to its original requirement helps company leaders identify ongoing risks. Linking test results to planned checks confirms that we met our goals. Popular apps like Google Maps trace tests of different map features back to customer navigation needs. This approach allows clear progress reports to stakeholders and enables early improvements. If requirements change later, traceability makes it easy to identify which tests are affected so we can make the right updates. It also supports thorough audits. Overall, traceability helps companies show software quality while managing deadlines for successful projects, from games to banking systems. Connecting all test documents makes the entire process more transparent and effective. Testing projects need people in different roles to keep everything running smoothly. The main roles are test management and testing. The test manager plans, monitors, and wraps up the testing process. They focus on the overall picture. For example, in agile development, the manager might share responsibilities with the development team, or an outside manager might coordinate tasks across multiple groups. The tester handles the hands-on technical work, like designing test cases, running checks, and finding bugs. Their main focus is on performing the tests. Different people can fill these roles based on the situation. A team leader, a dedicated test manager, or a developer manager can take on the management duties. In smaller projects, one person might handle both management and testing. Popular apps use specific roles to ensure quality, such as UI testers for software interfaces and automation engineers for software suites. Having clear but flexible roles helps streamline the testing process across industries, from games to banking. All testers need strong communication skills to effectively interact with others on the project team. Finding bugs means potentially delivering bad news, so being tactful and thoughtful is important. Really listening to feedback from others and clearly explaining test results is essential. Testing also requires a keen attention to detail so nothing gets missed, even small issues. Being methodical and thorough in checking every part of software helps ensure quality. Other important skills involve problem solving. Testers need analytical thinking to come up with creative ways to evaluate applications. A curious nature helps think outside the box for thorough testing. Domain knowledge about how programs will actually be used helps determine realistic tests. Technical know-how helps optimize the testing process, such as using automated tools. Focusing communication on constructive feedback rather than blame when issues arise is key, since testing supports the overall project success, not just pointing out flaws. The best testers skillfully balance all these abilities to thoroughly and professionally evaluate programs people rely on every day. When testing software, it's important for everyone on the project team to work closely together toward the shared goal of quality. Instead of working in isolated silos, a team approach encourages collaboration. On agile teams that follow extreme programming principles, any member can take on tasks they are qualified for, promoting flexibility. Everyone shares responsibility for ensuring the software functions well. For example, testers might partner with business experts to design acceptance tests that reflect real user needs. They could also collaborate with developers to agree on the best testing strategy from the start. This exchange of quality knowledge benefits all roles. When possible, working in the same location makes informal discussions and information sharing easier. Team members with different skills can support one another. Popular apps rely on diverse groups that integrate their specialties. Game testers might work alongside designers, while automated checks require collaboration between developers and QA. However, for critical systems like medical equipment, some separation of testing duties is necessary to maintain the independence needed for thorough safety evaluations. Overall, a team approach strengthens collaboration where appropriate. Getting different perspectives on software testing is important for catching various types of bugs. However, there are pros and cons to the independence between testers and developers. When developers test their own work, they are familiar with the code and can quickly find many issues. However, outside testers often spot different kinds of failures. Most projects benefit from varying levels of independence, such as internal test teams checking work across different developer groups or customers performing acceptance tests from their unique viewpoint. Independent testers can verify assumptions and challenges made during design and development, which often uncovers more bugs. However, too much separation can lead to poor collaboration between testers and developers. Popular apps use different balances. For example, at Nintendo, developers test each other's code, while external beta users catch usability issues that might be missed internally. Google automates much of its testing but also relies on outsider feedback for its search algorithms. Overall, a combination of independent perspectives along with open communication is ideal for ensuring thorough and efficient software quality across industries.